Hey guys, I'm Belize,
And I'm Savin.
and we're going to talk about DFT, or discrete Fourier transform today.
Cool. So, Belize, what is a discrete Fourier transform? Also, where's Sid?
Oh, Sid is gone.
Sid's gone? Sid's gone.
Yep, so it's pretty much just going from time domain to frequency domain.
Cool. So what does a frequency domain actually mean? What does it mean to be in the frequency domain?
So essentially, we're decomposing signals into its substituent frequencies. So as an example, what would the frequency domain representation be for a cosine signal?
Well, a cosine has a pure frequency, right? So I'd say it would be probably just one frequency, or depending on the math works, two.
Yeah, so what about the other signals though?
Well, I guess if you could decompose it into a bunch of, cosines and sines and stuff like that, then it could also have a frequency domain representation, right?
Yeah, so according to Fourier, any periodic signal can be represented as sum of sinusoids. So since we can see cosines as one pure frequency in the frequency domain, so that would be just like a bunch of frequencies that constitute the signal in the time domain for periodic signals. Perfect. So this is just like pretty much just change of basis. Also, why do we do DFT? What are the advantages of DFT?
The advantage of the DFT, I guess it makes some of our life easier, right? Like we can see things in the frequency domain that we can't see in the time domain.
Yeah, sometimes it's more informative in frequency domain. Can you give an example why you would want to look at the frequency domain representation of a signal?
Well, the frequency domain tells us a lot of interesting things about, composition of the individual frequencies. I guess an example is audio, right?
Mm-hmm.
You have a bunch of frequency domain coefficients that are large, and that low frequency range would indicate lots of bass, or in the high frequency range would be lots of treble frequencies. So it tells you a lot about the sound signal is a good example.
Right, yeah, exactly. So one example can be designing filters, right? So if we want to design a low pass filter or a band pass, whatever, that is again can be related to audio. You would want to look at the frequency representation of your signal and see which side you want to suppress, or which bass, or which means lower frequency you want to more pronounce. Then you would design the filter accordingly. Okay. Also sometimes in terms of storage or computation, it can be useful. So for storage, let's say you have a periodic signal and it's super complicated in time domain, but it actually is composed of 4 different frequencies in the frequency domain, so you only need to store 4 spikes, which is actually really easy, and you would have the full information of the signal. What I mean by computation is FFT, which is fast Fourier transform, which can be computed in n log n time instead of n squared. So it's sometimes better to do analysis for systems, if when you input a signal and trying to analyze the output, it might be easier to do FFT.
All right, yeah, those are some pretty good reasons.
Okay, so all right, we said it's a change of basis, so I guess we need to define what basis vectors we want to use. So we call them UKT, and let's say we are working with a length n signal, and then it would be a bunch of complex exponentials where k is going from 0 to n minus 1. So why do I have n different basis vectors?
Well, if your vector space is of size n, if r to the n, then you would need n length signals to your basis needs to be of length n to represent it.
Right. So we also choose them to be orthogonal. So which is actually really useful while like analyzing, because you can actually just like project your time domain signal onto the basis vectors, and that would exactly be your coefficients. You wouldn't have that if they were like only linearly independent, right? So UK form an orthogonal basis. Cool.
They also have some other cool properties, right? Like they're orthonormal, so they're all like, you know, they're normalized and orthogonal to each other, form the full, you know, they span the entire linear space, the vector space. Yeah.
Cool. So yeah, so we can represent, so this is my time domain signal as a linear combination of my basis vectors. Okay, so I'll...
Yeah, and we're going to underline to indicate frequency domain basis.
Cool. So, yeah, in that case, x, big X, or like underlined X, will be the frequency representation of the signal X. Or you can say, like as I mentioned before, you can write big X as the inner product of time domain signal with the basis vectors up to x and minus 1. Cool. All right.
If we wanted to make that into a matrix multiplication, right, like you know, a linear transformation, then we would write it, you know, we'd have to put these guys into a matrix of some sort, right? So we'd say, you know, x is f big X, right? Where f is our Fourier transformation. So if we were to write up this matrix, it would just be composed of all of our u vectors. So you end up with a u0, u1, u2, etc., all the way to u of n minus 1.
Yeah, perfect. I mean, it's just like the same thing, right? Like you're writing as a linear combination, and like if you just like pattern match this, then yeah, because like this thing is going to be x big X of 0, for example, right? Cool. So what if I wanted to go from the time to frequency? So how would I calculate big X with this linear system?
Well, we just take the inverse of the F matrix, right? And the F matrix has this nice property because it's an orthogonal basis that this F matrix is unitary. So F star F is equal to the identity. Or, yeah, this is also F star. Let me just write this as unitary. Great. So we got that. So, you know, using that property, we can do change this into f star times x is equal to big X.
Yeah. And what is f star, if you can remind me?
Well, f star is just the Hermitian Hermitian conjugate? The Hermitian of the... Anyways.
I think that's a thing, yeah.
Yeah. So instead, it's just the transpose and then the complex conjugate of the transpose. So u0, u1 star, it's the un minus 1. Awesome. Looks
right.
like that.
Also, like, I mean, it's good to point out that, like, I think this is obvious from this equation, but, like, f inverse is equal to f star. So this is a good property for unitary matrices, which you can see from the equation. Also, okay, let's switch here. You can write f as 1 over square root of n, 1, 1, 1, 1, 1, 1, 1, omega squared up to omega n minus 1, omega squared, omega to the 4, okay, omega 2 n minus 1, so up to omega n minus 1 and minus 1. So if you write it this way, then omega is going to be e to the j 2 pi over n. And the reason why I can write this is, remember, UK's were just like 1 over square root of n, e to the j 2 pi over n kt. So that's where the exponents come from, right? Like which one is coming from k and the other one is coming from t.
Great.
Okay, so one useful property is the conjugate property. Which is UK is the conjugate of U minus K. And since we can see them as like going around the unit circle, we can say this is also equal to UN minus K star.
Great.
And if xt, our signal, is real,
then we can use this conjugate property to prove conjugate symmetry.
yeah, so in that case, xk is going to be the conjugate of n minus k.
Cool.
Cool. So there's one thing that like keeps coming up in discussion sections, and we just want to make it clear. So let me just write example where we have, just gonna give it an amplitude too.
Let's make it a sine this time to change this up. I think we've beat cosine to death, right? Makes it more interesting.
Okay, yeah, for sure. I mean, there's gonna be like J's and stuff, so it's gonna like
That's
be
fine.
a little. Okay, well, let's define omega as 2 pi over n k naught, where k naught can be anywhere from 0 to n minus 1. Okay, so how can I write sine as a sum of exponentials? So at the end of the day, we're like trying to figure out, yeah, I didn't form the question, sorry. So we're trying to figure out the DFT coefficients of the signal, okay?
So x of k equals
What? Okay, so how can I write this signal as a sum of exponentials?
Well, Euler's identity is pretty nice here.
All right.
So we can say that, a sine is e to the j omega naught t minus e to the minus j omega naught t over 2j, right?
Oh, where did the j come from in the denominator?
Did I screw up?
No, you're right.
Okay. Okay. All right. Yeah. Well, the j comes from the fact that e to the j theta is equal to cosine theta plus j sine theta. Therefore, we have to get rid of this j somehow, and we divide by j.
Perfect. Yeah, that's right. So, okay. So if we know this, we're at the end of the day trying to like pattern match it to the coefficients of UKs, right? So we can like write omega naught as okay, I'll go one step further. I'll say e j 2 pi over n k naught. Wow, my writing is great.
It's better than mine. I'll give you that.
E to the j.
Dude, I have to
2 pi
erase your
over
discussion
n.
notes before I do mine, and it's just like yours looks beautiful, and I start writing over it, and then I think my students are like, you should have just left what was written there before.
Lols. But actually, I'm gonna go ahead and like I'm writing the same thing. I'm just like I was just gonna sub k naught, but whatever, it's fine. So okay. So how do I go from like UK to this? Like how do I know what the coefficient is? I guess as a reminder, I can like write it here. UK t was defined as 1 over square root of n e to the j 2 pi n kt, right?
Mm-hmm.
So 2 pi over n k naught is omega naught. So in that case, how would I match this expression, to that?
Well, so it looks like we're just off by a factor of root n, right? And then
Pretty much, yeah.
yeah. So I could take this guy, this first term, and write this as a over 2j times root n.
That's right, yeah.
U of
K naught, yeah.
K naught, yeah. T. Get rid of the t. Minus a over 2j root n u of minus k naught.
Yeah, perfect. Or like n minus k naught, which is the same thing. So I guess like you guys are gonna see if you like take 120, that like j term is just like a like phase delay. So like it doesn't like you don't need to worry about like the j factor for now.
Also, there.
Okay, so well, in that case, we learned that like we can write the time domain x as a linear combination of the DFT coefficients and the DFT bases, right? So the coefficients I have is just like pretty much these guys, right? So in that case, xk is going to be a square root of n over 2j, where k is equal to k naught, and a minus a square root of n over 2j, where k is equal to n minus k naught, and 0 otherwise, right?
Great. So one thing to note is that this is this pesky root n term pops up a lot. That root n term is kind of going to change a few things about your signal. Like if you increase the sampling rate by a factor of 2, you'll notice that your x of k coefficients all go up by a factor of root 2. So although it might be the same signal, it actually gives you a slightly different answer. So just things to note when you're doing problems.
Well, you can like think about it this way, right? So like sometimes like you are not gonna have amplitudes that are like as clear. So like if you have like a bunch of different frequencies and you need to like threshold at some point, the more samples you take, the more amplitude you're gonna have for the x of k. So you're gonna like make like completely sure that is like the frequency that you want. So like, I mean, sometimes you're like oversampling doesn't like make a difference, but in some cases it might actually help you. All right. So moving on. So we talked about, okay, let's, I guess, like move on to DFT and LTI systems. What is an LTI system?
Linear time invariant, right?
Right, and like all of this analysis like works if your system is LTI. So for this class, we're only interested in LTI systems. Linear is like your like old like linear that you learned in 16A, scaling and like addition, and like time invariance is if you time delay the signal, your output behavior shouldn't change, right? So okay, let's define the impulse response. What is an impulse? I mean, in this context, I know what an impulse is.
Well, an impulse is, I don't know, a spike, kind of. I guess you'd call it a spike at a specific time.
Okay, so for a discrete time impulse, or like we call it like Kronecker delta, I can, wow, I'm great. Okay. 1 when k is 0 and 0 everywhere else. Also, this like thing is otherwise if you like are not in my section or don't know. Okay, so this is delta k, and if we send in to the system h, the output we get is the impulse response, which makes intuitive sense because like the response the system gives to the impulse is called impulse response, right? Okay, okay, so how would I generalize it to like any input, right? So I can like write x t as bunch of scaled and shifted deltas.
Super.
Okay, if I know that, and if I know my system is LTI, what can I say about the following system? Also, like, sorry about my handwriting. I know it sucks, but it's okay. So if you have an output y and an input x, what can you say about the convolution sum?
Well, I guess that we could say that this guy, I mean, this just kind of looks like using our LTI system properties. We know that all of these deltas turn into h's, right?
Right. Yeah.
So all of these deltas become h's, and because it's time invariant, these time shifts just mean that the output is time shifted too. So your y of t would end up being a sum. Sum from k equal to 0 to the length of the signal. We'll call this guy L, right?
Sure. Yeah.
Call that to L of x of k and h of t minus k. Okay, and then here we'll say that L is the length of X.
Well, okay, this would be L minus 1 then. But
Oh, sorry,
okay,
yeah. L is the length of X. M plus 1, well, the reason for that is, will be clear in a second, is the length of H.
Mm-hmm. So I guess like the length of the output is going to be sum of the length of system in the signal, a minus 1, because it like overlaps at 0. But I mean, it's not super important. But like L plus M is going to be the length of Y.
Off by 1 errors, man.
Yeah, don't use MATLAB. It's okay if you use it. So we define the lengths because like when we are defining the circulant matrix, we want to match the size. So like we're going to 0 pad the system and the input. So you don't have to do that, but like it's just like nice to like use the properties of circulant matrices, which we're going to talk about right now.
Circulant matrices are great.
Okay, so if we define this convolution sum as a linear system with matrices, then you're going to have y of 0, y of 1 to y of m plus L minus 1. Okay, and then you're going to have some matrix here, and you're going to have your input that is 0 padded to match x of 0, x of 1, up to x of L minus 1, and a bunch of zeros. Okay. All right, so I'm going to need to simulate this convolution sum into here. So how would I construct the matrix?
Well, if we want to find y of 0, right, we know that y of 0 is just the sum k equal to this of h of minus k, right? X of k, h of minus k from k equal to 0 to L minus 1. So
yeah,
that kind of looks like, you know, this guy, right? If we're going down the columns, this first guy ends up just being the impulse response, right? Because that's what you multiply by the x for each component. So you have this h of 0, h of 1, h of, all the way to h of m. There we go. And then a bunch of zeros to fill it in, right? Because square matrices are good. This guy, since we're doing time delayed by 1, we also time delay this second column by 1.
Right, yeah.
So h of 0, h of 1, all the way to h of m, and then also zeros. And this last one is a 0, and so on until this last guy. We keep, you know, shifting it until we end up with h of 1, a bunch of zeros.
No, h of 2 and stuff.
Oh, sorry, yeah. H of 2,
Whatever,
so on. This last one is h of 0. You end up with h of m over here somewhere, and zeros.
Yeah. I mean, it's okay if you like didn't like couldn't come up with the matrix construction, but it's just like translating the convolution sum into matrix form. So y is okay. This is a circulant matrix. What is a circulant matrix?
Well, it's a matrix that follows this kind of form, right? Where each column is the shifted version of the column right before it.
Right. Yeah. And circulant matrices are really useful and related to DFT because turns out that DFT basis, which is UK's, as you remember, or will remember by the final, diagonalizes circulant matrices.
That's crazy.
Yeah, that is actually really useful, turns out. And the way you figure that out is, so if I like left multiply the equation by f star, then I'm gonna get f star y f star ch, and I know f star is the identity, so I can just say f star here and x. So this is the frequency representation of x, this is the frequency representation of y, and turns out this is a diagonal matrix, which is like super useful.
Very
Perfect.
useful. So we have this matrix, y times x. And the form of this matrix actually takes is the following. So you have h. What I'm going to write is h of 0, h of 1, and then all the way to h of L plus m minus 1.
Mm-hmm.
And then zeros in the corners. And what's happening here is this actually has a root. Has a root n there.
Or like m plus L in this case.
Yeah. Geez. Sorry, I'm used to doing n because like n is just traditionally what. Anyways, making excuses because I'm bad. Okay, so this matrix has a L plus m, and then these are this vector is the Fourier transform of my impulse response that I had before. That's cool. The diagonal entries are literally the Fourier transform of the original impulse response we had. So like we save so many steps by just doing it this way.
Or like zero padded in this case. But
yeah.
Yeah. Mm-hmm.
Yeah. Sorry. This should be the zero padded version. Zero padded version. I should make that clear.
So I guess like what we're trying to say is like if you were to take the first column of CH and transform it to the frequency domain, then you would get the big H's going from 0 to m plus L minus 1. That's essentially it. Okay, good. So what does this say us about like the eigenvectors and eigenvalues of the matrix we have, I guess?
Well, it tells us pretty something nice that like basically we can write C sub h as f h f star. So this is basically the same thing as that statement right there. Diagonalizes the circular matrix.
Are we switching notation from here? Oh, yeah, you're right.
This is C sub h, not C h.
Yeah.
Yeah.
Okay, so cool. How can we find the DFT coefficient for y's given the DFT coefficients of h and x if we know this thing?
Yeah. So given that, we can say using these properties, right? We can say that y is equal to root L. Let's call this L plus m of h. This is pointwise multiplication x.
Yeah, so, or like in other words, what we're saying is like, let's see if I can get this. Y of k is m plus L h k times x k. And I mean, there's like no magic here, right? Like we're pretty much just saying that like you're multiplying this like h with the DFT coefficients of x, and like as you can see, like everything else is 0 other than like h0 for x0, for example. So like y0 is just going to be square root of m plus L times h0 times x0. All right, good. So we're gonna do an example from a discussion right now. Oh,
Yeah.
nice.
Sampling matching. All right, let's do it.
Okay, so what do we have? We have a time domain signal that we sample with a frequency 3 hertz.
This is important.
Okay. And they're asking us about the DFT coefficient. So like in these types of questions, like you just like list what you already know. So we know 3 hertz, and we know that we sampled for 12 seconds.
So t equals 12
Okay.
seconds.
So how many samples do I have in this case?
Well, 3 hertz, 3 samples per second, right? So we have 12 seconds times 3 samples per second equals 36 samples.
All right, like first things first, right? Like the number of samples you have should match the number of points you have in your
Right.
the frequency domain graph.
So this guy is n. So yeah, the number of samples, you don't lose samples between your frequency domain and your time domain, so that's why you still need all of those samples.
Okay, so also like why do I have like 4 spikes here? Like, I don't know.
Well, I mean, the 4 spikes are the ones they gave us, right? Oh, sorry, 4 spikes here, not 4 periods.
Yeah. 4 spikes of it.
A little frazzled. Okay, so 4 spikes, well, that would imply that there should be 2 different like cosines or 2 different sines, right? Well, we know that this is a real signal, right? Because they don't tell us there's an imaginary portion. And by conjugate symmetry, so conj symmetry, there are 2 frequencies present.
Right. If you like remember the xk's that we did, we said we had non-zero elements for the DFT coefficients for k and n minus k, which is actually just like minus k. We just like do plus n because it's like mod n. You can like also say 2n minus k, like it's fine. But like what we're saying is like in a cosine or a sine, you have a non-zero spike at positive frequency and at a negative frequency. So how do I find that point k?
Well, we have to look at the frequencies present in our time domain signal, basically the periodicities, right? So looking at it, right, I see 4 periods of this big signal, right? So the big signal corresponds to the signal with the highest magnitude in the time domain and also should be the highest magnitude in the frequency domain, right?
Right, yeah.
So if I looked at this, you know, you could kind of see this playing out. And this is very rough, I will admit.
Yeah, we don't really know.
We do not know. We don't know what it is precisely, but we have a rough idea. Let me change colors here.
Oh, fancy.
And then we can kind of see some like other stuff going on. That is butchered. Let me try that again.
Okay. Yeah, I mean the point is it's just like faster, therefore we see more periods of that signal.
Yes. Yeah, perfect.
Okay, let's start from the bigger amplitude subsignal. And okay, if we start from that, how do I know like where the point K is? Big amplitude.
Well, we know where the signal is based on the frequency of that signal, right? Okay. So we got to calculate the frequency from our period, right? So I have I guess a different way from Belize. So you know, we'll do my way first, and then we'll do Belize's way next.
Yeah.
So what I like to do is, okay, so there's 12 seconds, and there's 4 periods, or there's 36 samples for 4 periods, right? So that means that the period of 1, so 30, not 26. So 36 samples and 4 periods. So that is 9 samples per period.
Okay.
And so that basically gives us the period of one sinusoid. So what we want is 2 pi over, let's call this guy t. So 2 pi over t is omega. So we know omega is 2 pi over 9.
Okay.
Okay. So now that we got this frequency, this is important. So we got that guy. The next thing we want to do is we want to match this frequency to a corresponding k value or a corresponding DFT coefficient. All right. So we know that UK 1 over root n e to the j 2 pi over n k t, right? So in this case n is 36, so you have 1 over 6 e to the j 2 pi over 36 k t. So we know that 2 pi over 36k equals 2 pi over 9, so k equals 4.
Perfect, yeah.
So that big amplitude corresponds to a k equals 4. So that
and
would,
minus 4, yeah.
Yeah, so k equals 4 and k equals minus 4. Okay.
Okay.
So we have k equals 4 and k equals minus 4. So this guy doesn't even have a k equals 4 or minus 4 coefficient.
Sad, okay.
All right, so we have those, and the next thing we want to do is sort of match an amplitude toward it, right? So we can kind of look at this.
I think it's just like leave C, but like if you had like 2 different options with
if we wanted to check it a little bit further, right? So we know that we have k equals 4 and minus 4, and these are the biggest amplitudes. That would kind of imply that it should be this guy. But we want to confirm that. So to confirm that, let's check what the amplitude should be approximately, right?
So if you just look at what Savin did roughly for the red signal, it kind of goes from 3 to -3. So its amplitude would be 3, right? Because we say peak to peak over 2, so therefore amplitude is 3.
So we'll write that the big amplitude is approximately equal to basically an A times sine of we had this guy, right? So 2 pi over 9t. Yeah.
Let's do cosine because this is cosine. Yeah.
Sure, cosine. I mean, both end up with the same answer, but yeah.
But
so,
it would be flipped magnitudes.
Well, magnitude is always a positive.
Oh, we take the.
Yeah.
Okay. Yeah.
Either way.
Sure. Yeah.
Cosine of 2 pi over 9t, right? So we decided that a is 3, so we have 3 cosine 2 pi over 9t.
Okay.
So we have, this is, from what we had before, 3 halves, just gives you root n over 2, 3 u of 4t plus.
And again, what he's doing is just converting cosine to sum of complex exponentials and matching those with the UKs that we have.
And this root n over 2 gives us a factor of 3. So root n is 6, right? So this is a 9 approximately, right?
Okay. Yeah.
Approximately u4 of t plus u4 of t plus 9u minus 4 of t. So
right.
9 corresponds to this. So we were looking for a 1 with 9 for its fourth coefficient, and this is the only one that does it for us.
Yeah, so in this case, you don't really care about the amplitude for the smaller amplitude subsignal because, there's no way to tell what the amplitude is. So yeah.
It's pretty hard for us to tell just by examining the signal of what that smaller magnitude is and stuff like that, or even its frequency, honestly. But yeah.
Cool.
Let's do another one.
Okay, so we have a time domain signal, which is a pure sinusoid. Okay, therefore we have 2 non-zero DFT magnitudes, and now we have a signal with 2 periods now. And we sample at a different frequency. I can see that it's more heavily sampled. Okay, so first of all, I have different number of points for A, B, C, and D for samples. Okay, so D seems like an outlier in this case, and if you actually go ahead and count the number of samples you have, what do we get? And I don't know, but it's definitely not 10.
Yeah, it's approximately n equals to 60, right?
Okay, this kills D.
Yeah, so this is n equal to 10, and this is clearly much more than that, not 110. 10, and this is about equal to 60. This is about equal to 60, and this is also about equal to 60. You could go through and count, but, it is 60. Trust us if you want to go through it afterwards.
Yeah. Also, if we look at the magnitude of the signal, we see something like 1.75 or something, and if we sample more frequently, then n is going up, right? And we know that the coefficients of, okay, let's do it, xk, I think we've done this enough times by now. It would be square root of n over 2 times amplitude for, okay, 0 otherwise, and it would be k or n minus k. Okay, or minus k, right? So, and the amplitude is 1, so it's just going to be square root of n over 2. Square root of 60 is what, 8? So 8 over 2 is 4. So we need to have a magnitude of around 4. So this kills A. It.
So we got those. And the last part that we gotta have to do is figure out what the actual frequency is, right?
That's right. So we had, So I guess like my way of doing it, which is like essentially Sovin's way, but like it's like more like a hacky way. So if you count the number of periods that you like see in your sample, that actually corresponds to the k that is going to be non-zero. So like since you observe a period, like one period in the signal, your non-zero coefficient is going to be at k equals 1. So since you observe 2 periods of the signal in the second case, k equals to 2 should be the non-zero coefficient. So I guess that kills B, and go with C.
So just to draw out what Belize said, so when we do these coefficients, right, you have your u0 is, or just write out u of k so we can see that. U sub k is 1 over root n e to the j 2 pi over n kt. So if we plug in values here, your u of 0 value is what we call the DC component. So basically, this is 0. You end up with 1 over root n. If I just draw this out, this is magnitude mag u0, yeah? So when I do magnitude of u1, it actually looks a little bit different. You actually end up, so for the time axis, this is 0, and this is n, when you're going through n points.
Sure.
So 0, n. When you actually do the u1, it looks like this, and this is magnitude, yeah, I wrote that already. So that's magnitude of u1, and that's what she was saying about the number of periods in the signal. Again, if I keep drawing your u2, magnitude of u2. Oh, also to note the magnitude of this, so this top point is again 1 over root n. Doesn't change. So u2, drawing it out, you end up with, this is gonna, can I do this? Is that right? That's
no.
not right. Nope, nope. Let me try that again. Okay. I'm not good at drawing.
It's okay. Okay, here you go. Yeah.
Yeah. So again, 1 over root n. So the idea is that, like, you know, you keep adding more and more and more until you reach your maximum frequency possible. So that was what she was saying about counting the number of periods in present in the signal.
Yeah, like what we're essentially doing is like scaling those like UKs, whatever it is, and trying to get our original sinusoid, right? So what we're doing effectively is like we would like multiply 0 and 1, for example, to get like for the second case, for these signals. So like this would not appear in the final signal, but like U2 would appear scaled, square root of n over 2, whatever, depending on what your amplitude is, like we said. But like you will still like see a behavior like U2. Therefore, you can just count the number of periods that you see. But you should still understand like what it translates to, etc.
Yeah.
I think that's all, right?
That's it. All right. Well, good luck on the exam. Thanks for watching.
Thanks for watching.